No, no, I know he's not here. No, no. Anyway, I'm going to go ahead and turn this furnace on. I've converted it to propane. Actually, I didn't convert this to propane. My buddy JC converted this to propane. Actually, I asked JC to install it to convert it to propane for one reason. Because if JC can do it, anybody can do it. Yeah. The meter, the 429 meter.
It's in my pocket, don't worry about it.
Where is that meter? We're going to be using that meter. Hello. Meter. Huh? There it is. All right. Okay, the very first thing that happened is the inducer fan motor started. So that means that our switch was open at first, right? And now the pressure has to close, or our hot surface igniter does not come on. So if a hot surface igniter does not come on, we need to check to see if that pressure switch is closed, right? Because we saw our sequence of operation, right? So it did close, obviously, and it lit, and it went all the way across. Now, if you look at my meter here, can you see what the output rating, the reading there is on the meter for the microamps? Is it on microamps? 2.8. Yep, 2.7, 2.8. That's 2.7 microamps. It only needs 0.5, guys. It's putting out 5 times as much as it needs. Does that make sense? If I got that kind of reading on my meter and my board was telling me there was a problem, tell me what do you think it would be? How about a bad board? It's the board. It's the board, yeah. It's always the board. But in this case, if you've got the right reading and the board ain't doing it, replace the board. Does that make sense? It's a very low reading, guys, and it's very sensitive board. And I've seen boards do this where it's supposed to be doing something and it's giving you a false positive. Does that make sense? All right. After it's lit, notice that I've got my manifold pressure at 9.75. This is propane. This is not natural gas. I converted this to propane, actually JC did. The outlet pressure, instead of 3.5 for natural gas, on propane is supposed to be between 9 and 11. Does that make sense?
Why is that?
Because it's a different fuel. It's a different oxygen and fuel mixture. It's just not the same. If you try to put propane on a natural gas furnace, what you will do is you will soot up the furnace so bad that you'll end up throwing it away in about a week. Natural gas gives you more heat per amount of fuel. It seems to get hotter. I think natural gas probably burns cleaner. I'm not really sure. But on the output, on the exhaust, isn't propane cleaner than exhaust? I'm not really sure. I haven't hooked up my combustion analyzer to propane. I've hooked it up to natural gas, but not to propane. So all those readings, I don't have in my head. It's a good question, because I didn't think of it. It's a great question. All right. The board does a couple of things, but what I'm going to do here is first take a temperature of going across my heat exchanger so you guys can see the readings. You see my temperature rise across my heat exchanger?
Where are they wired?
Just a little thermocouple. It's just sticking up in there, and I just got it stuck in the return. Simple. Does that make sense, guys?
See what it looks like on the outside?
Huh? It's right there.
Is it like a sensor?
It's just a thermocouple. It's just a wire, thermocouple wire. There's the K-type thermocouple.
Read it.
Make sense? Easy. And you can see what our temperature rise. If you hit this mode, it'll tell you. This is giving me a 24.6 right now. temperature rise. And as I leave this on longer, it'll get warmer and warmer. Plus, on this board, I can control my fan speed on this board, and I can actually change the fan speed on this board very easily by doing this. While it's running. No unplugging wires. I can literally push that switch right there on that and change that fan switch from high, medium low, and low, just like that. And when I do that, my temperature starts dropping in my heat exchanger. Remember we had a discussion about how much air we want moving over our heat exchanger? Guess what? We start moving a lot more cold air. Our rise on our heat exchanger goes down because we're moving more air. Does that make sense? All right. What I'm going to do now is, since we've seen all of this operating and we've seen that, now we're going to go to air flow. Okay, I'm going to measure air flow and how this manometer checks air flow. All right? Turn this off. And I'm going to put the plug back into the gas valve because I'm going to use this for a different thing. And what's nice is Honeywell uses their service, you know the plugs here, the little plug that plugs up the hole? It's the same diameter as your refrigeration service wrench. It's the same size, so you can use that service wrench on your little ratchet, you know, that you use to open the valves on the air conditioner. And they work really good together. Does that make sense? I like that. I think White Rogers does not use the same size, but Honeywell does. All right, I'm letting this go all the way down before I plug this up. Any questions, guys? We've gone through the sequence of operation. We've looked at the flame sensor. Oh, while this is cooling off, I want to say something. When you clean the flame sensor, because the flame sensor does get dirty with carbon because it's in the flame, right? And so you can get particles of carbon on the flame. The way that it works is, it's called flame rectification. As the voltage is 120 volts, it's sending out through this wire to the flame sensor, but it's very low current, microamps. So what happens is, as the flame is going across that rod, the particles of carbon will convert it from AC voltage to DC voltage because it only allows one side of the sine wave to be gone to ground. It's called flame rectification. So it converts it from AC to DC. That board knows that. And that board is calibrated to see DC volts. That's the way if you tried to jumper that, it wouldn't work because it would be AC volts. Does that make sense? Yeah. So they use that flame rectification for safety. If it didn't see what it wants to see, it ain't gonna go. If it gets crappy and dirty, use this stainless steel toothbrush that we sell for like $3, and every technician should have one in their tool pouch because you use it for everything. Do not use a dollar bill. Do not use sandpaper. The reason is it leaves a residue on the rod, and that residue, when you put it back in the flame, will become burned and leave more residue. This doesn't leave any residue, and it's cheap. And I've done service calls where all I've had to do was scratch this with this toothbrush, and that's all I had to do. You just get in there and you scrub it, basically. Some of them you get to really easy. This one you can't get to really easy, but it's only got one screw. It's got one. You got to remove the rod on this one. Some of them you don't have to. It depends on how easy it is to get to. Does that make sense? No sandpaper. Here's what happens. The silica gets deposited on the rod. The silica, right, Oscar? That silica then, in particles, in microscopic particles, gets kind of, I don't know, burned into the metal rod from the flame, and it becomes more insulated because the silica creates a microscopic coating. And while it'll work, it won't work as long and you'll have to clean it again, and then you'll have to clean it again, and you'll have to clean it again.
Sounds like a barbecue grill, man.
I know. Use the stainless steel brush, guys. It doesn't leave anything. Right, Oscar? Oscar's one of my colleagues, by the way. Yes, it turns into glass. The silica turns into glass, and glass is an insulator. All right? That makes sense? All right. I'm going, would you hold this? I'm going to put this plug back in.
You need a technician?
No, it's just that it's tight. There we go.